slightly disconnected again.
If you have radius. Okay, so another big moment has arrived. I'll write down the first Feynman diagram of quantum electrodynamics to show eyes and dots and everything. So here is the diagram.
I'm not going to use this already.
So here an electron comes toward with momentum P.
You're turning it in.
Yeah.
And
some people use the graded ones.
It splits into a photon.
No, this is the graded one. They're all graded.
And photon is reabsorbed. Photon can have any momentum k. You'll integrate all intermediate states as you always do. And we'll choose that momentum goes that way. That's just a convention.
No, what about the ones we need to now?
And then by momentum conservation, here the momentum will be
People that can graded with.
P plus k, flowing this
I only
way.
got one stack for me.
And when they come out, add P plus k and minus k, and we come out with the same momentum. So that's the first virtual correction to electron, and it's called electron self-energy or something. Self-energy. That's the beginning of getting an electron dressed up. It's charged, so it can emit photons, reabsorb them, and it can emerge as a single photon. And this turns out, in a way that I will not discuss here, leads to renormalization of coupling constants and masses. So these things will be interpreted as a change of the effective mass of electrons when you add them all up. You've kind of seen it because when we went from our our connected graphs to one particle reducible graphs, we show that there is a propagator which is a sum of all graphs of this kind that cannot be cut up into smaller pieces, one particle. So this is the beginning of the calculation. So now we have our rules. So now we can write out what the thing is. So this is a mass shell thing, so it will have an U. And this is coming out, so that will be an U times. So that's a projection that makes sure that we're looking at it on the mass shell. Then there will be electron propagator here, and we have it. So this guy here is I P slash plus M divided by P squared minus M squared plus I P. So that's what propagator for electron is between two collisions with the photon. The photon will make very easy, will be just minus I G U. It has squared momentum, which is just k squared, and the mass has been set equal to 0, so that's all for this guy. And then we'll have two vertices, and according to our rule, the vertex is I, E, comma, U. That's matrix that couples three representations of Minkowski group. Delta 4. And here we have a statement that K plus So let's call this, P2 or something, P1. K plus P minus P1 is 0. And we'll have a similar thing here. And now we have to sum over all intermediate states. And in this case, these are states where the momentum has different energy. Because the momentum could be maybe just kicked off slightly, or maybe you produce a huge energy momentum and then we combine with it. So all of this has to be added. So the calculation with this diagram summary just for you is this diagram. Once you draw this picture, that's the same thing as saying U of P, that doesn't get integrated over, it's fixed. Then you have an IE coupling strength twice because there are two vertices. Then you have to integrate, and then there will be I think I might have got an I that I didn't want to get. There will be an I for this propagator here. My notes, unfortunately, haven't. Then I have to integrate over intermediate momentum. And now I have two Dirac delta functions in momentum, one for here, one from there. So there were two integrations, but one of them goes away. I integrate over this P1 and I integrate over K, but then I use one of the delta functions. So that goes away. And I get, and the other delta function is used to ensure that when I come out with P. So I get minus G mu for the photon. So that's contribution of this guy. And then I get two matrices. So this is mu and this is mu. And I get Dirac matrix that couples me with the incoming mu here. Gamma mu, we contracting the delta function, then I had to put a propagator, and if these things don't commute, it's very important to keep track of that. So, you look at it and you see when K is small, this will be P squared will be close to M squared. And, we know that P is on the mass shell. So for small k, I'll get something called infradivergence. When I actually compute this integral, I'll notice that there's some problems with this integral. And when the k is very large, then these guys, and also when k is small, this also goes small. So we'll discuss this in more detail, what the various limits of this integral are. But when k is very large, it's dominated by 1 over k to the 4th. So that's small contribution. So everything contributes, photons of any energy imaginable, time-like, space-like, doesn't matter, they all contribute. If you were doing time-ordered perturbation theory, then you would have to write diagrams that would look like this, for example. That you go and then you emit something, and that will be a different contribution from this process. So here what happens, you're coming in time order perturbation field. Perturbation field. You go and you emit something, and you propagate in time, you have particle, antiparticle, and they recombine. Or you go and you suddenly collide with a photon and an antiparticle here, while this guy was created by the photon. And these things can both contribute. They're both Feynman diagrams of time order perturbation theory. So when you do condensed matter, this actually you have to do. So, you get very ugly diagrams. But relativistic quantum field theory is wonderful because they're both subsumed in this. Because that was, the exercise, bonus exercise 6 for David Benjamin objective. But, it's amazing. This thing falls together. And we'll now discuss this. So let's see, I got all this. You exchanged 11s and signed off on them, and I got a piece of paper from somebody.
Oh, it's still going around.
Still going around. All right, that's it. Maybe next week, magnetic moment. Magnetic moment for Thanksgiving.
So for this diagram, what's happening in space? Like, what is the picture of this process?
The picture is the same, it's just that the propagators tend to be harder to compute because they're not easily inverted. But it's the same picture.
So if at a point an electron has emitted a photon, how can they meet again if they have different...
That's the wonder of quantum mechanics.
So
No, that's easier to understand in space. Basically, there's an amplitude that propagates and creates something through interaction term. So there are two amplitudes, and they combine, and they create something. So, it's actually, I think it's easier to think of this in real space-time. The only thing, when you think about it, you'll naturally think in time-ordered way, being a human being, but relativity says you can add them up and you get a simpler formula than either one of these guys.
So they don't have to be spatially close to each other to interact?
No. Quantum mechanics violates such things. Anyway, so now it turns out this is useful because this E square that we have here, it shows us number, E square, is a small number. And that's a small correction. So that was, it took 15 years, but there was a second row in between. It took 15 years to go from Dirac equation to this correction. And the young people took over and they did everything right. The old people couldn't do this. The heroes of the series could not do this calculation. Okay, that's it. Can you come back to me?